Welcome to our April Astronomy Club of Akron membership meeting. I'm very happy to introduce our speaker, Gary Kader from Baldwin, Wallace College. Gary's been out a number of times to talk to us for probably about over a decade. He's been coming out to talk to us. So let's have a hand for Gary.
Thank you. I've been here so many times, I should become a member. Okay. All right. My apologies to, oh shoot. His name just went out of my head. The guy in the wheelchair, died recently.
Stephen Hawking.
Stephen Hawking, yes. On a brief history of time. So this is a brief history of the history of time. Okay? And so we're going to talk about the question, what time is it? And after tonight, you're not going to have a clue what time it is, okay? After I explain all this stuff to you. It's all about the motions in the sky, keeping time. Okay, that's where it all started. So astronomers have always been the timekeepers, which is kind of nice because that was we were the ones that were able to predict the growing seasons and predict floods and all that. That gave us power. Okay, so here's what we're going to look at. I'm going to look at some prehistoric timekeeping. We're going to talk about what is a day. We're going to talk, of course, what time it is. What time is it? Why are there 24 hours in a day? Where did that come from? And why are there 60 minutes in an hour, 60 seconds in a minute? Where'd that come from? What's a month? You're going to be happy to know that there's about 5 different ones. Okay. What's a year? There's about 5 different years, so we can talk about that. And how our current calendar became what it is, how we got here. And then at the end, I'm just going to talk about Julian days because we all run into that in astronomy, and I'll talk real quick about where that came from. So, early civilizations, they studied the universe, so what they could see with their naked eye. And they saw patterns, and so they could use them for a lot of purposes. Number one, they could use them for timekeeping. They knew that, every time, in Egypt, every time Sirius would rise at the same time the sun was, you knew the Nile was going to flood in a few weeks, that sort of thing. And so you could work your agricultural calendars. You certainly didn't want to plant your plants 2 weeks before the Nile flooded, okay? And then navigation, and of course ceremonial. And one of the more famous ones, of course, is Stonehenge. And we'll talk about that in a minute. So they observed the sky, they saw these patterns, and decided to keep track of them. So Stonehenge was made somewhere 2800 to 1800 BC. It's the oldest timepiece in existence, and it was designed from astronomical observations. It's in the south of England, if you've ever been there. I was in England once, and unfortunately my time didn't allow me to get down there. I would have liked to have gotten down there. They were able to help predict eclipses, that sort of thing, and of course the phases of the moon. And it was aligned to the solstices. I think you're all familiar with what those are. One of the problems, though, is when we introduced daylight savings time, we had to give this thing a little bit of a turn to the left.
I like it.
Okay, so the first thing we did with, humans did was sundials. All these Egyptian obelisks and stuff that you see if you go to Europe that were all stolen out of Egypt, those were all sundials. Okay, they were put in the city square, and that's what they were used for. The Nigerians actually looked at the crescent moon and how it was, rotated to determine when the rainy season was going to show up. So that's what they did. And then most of you have probably seen this. This is the Sun Dagger in New Mexico. And if you've ever been down there, you can in Chaco Valley, or Chaco Canyon, I think it is. There's this light that shines right down through the middle of that pattern in the winter solstices and the equinoxes. And of course, Machu Picchu, which is on my bucket list, haven't been there yet, but it's going to be, is almost all astronomically related. as far as the location of the buildings and monuments and what have you. A lot of alignments with, particularly Venus. They were really, really obsessed with Venus for some reason. So the priests made their observations and what have you, their calculations that enabled them to, do some predictions as to when they should plant stuff. And of course that, gave them religious authority and temporal power, that sort of thing. And of course you all heard about the Mayan calendar. By the way, you're all dead. I mean, the world ended on 2012 on December 21st because the Mayan calendar ran out, okay? It just reset, okay? You have no idea how many calls I got from radio stations, from TV stations, and all that other, it was amazing. Anyway, it was actually based on 260 named days and a combination of 365 days in the year, so it was a little weird. I won't go into the details on it, otherwise we'll be here all night. Okay, so let's look at what is a day. A day is local noon to local noon. Okay, so as I think you're all familiar with the meridian. That's that line that cuts the sky, the north-south line that cuts the sky in half. And as the sun is approaching the meridian, it's ante-meridian or AM, and as it goes past it, it's post-meridian or PM. And so the apparent solar day is two crossings of the mean sun. Not mean that it's angry or anything, okay? Mean that it's average. Because, I'll explain a little bit later, excuse me, that sometimes the sun gets there a little early, sometimes it gets a little late. It's called the equation of time, and we'll explain what that's all about. You can actually excuse me here. A little bit of water might help.
Yeah, she's got it.
Sidereal day. Thank you. Anytime you hear the word sidereal, that means relative to the stars. That's what that word means. And so that's the crossing of two stars. That's the true rotational period of the Earth. 23 hours, 56 minutes, and some change. So, we're going to come back to that, and then I'll talk about the difference between the sidereal day and the solar day in a few minutes. But let's talk about the 12 hours in a day. That came from the Egyptians. The first sundials, they were stakes placed in the ground, and they measured the shadows, that sort of thing, and they calibrated it into 12 parts. And so they used the Dewey Decimal System, or base 12. We'll talk about base 60 also. That was the Mesopotamians. And it was attributed to the fact that there were, 12 lunar cycles in a year. Also, counting the digits of your fingers, and I'll explain that, okay? But although the hours in the day, during the day it was broken up into 12 equal segments, the hours weren't always the same, because during the summer, the day was longer, and so the hour was longer, because they just wanted it in 12 easy pieces. So this is how this works. You get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12. And so that's where the base 12 came from. Our base 10 came from the fact that we've got 10 digits. Darn. So the Egyptians regarded the sunlit portion of the day different from the nighttime portion. It wasn't a day, this is the nighttime portion, totally different. And so the nighttime was broken up into 12 pieces also. And they had 36 star groups that they used to do this. And so they actually produced tables for all of this so you could tell time at night. In fact, they found them in the lids of coffins of Egyptians, on the underside of the lid, so apparently the dead could tell time at night. So you had these 36 stars, and they divided the heaven into equal parts, and so there were 18 of them. All right, if you divided it by 2. But they set aside 3 stars for the morning twilight and 3 stars for the evening twilight. That left you 12. And so that's how they got the 12 segments of nighttime. That's where the 12 hours of night came from. So hence our 24 hours in a day. All right, I think you all, so that's how our 24-hour day came from. They came up with it, like so many things I tell my students, we didn't invent this stuff to confuse undergrads. Okay, that wasn't our intent. It was somebody else invented it, it worked, why don't we just stay with it? So we inherited this, it works, let's keep it that way. The same way with subdividing angles. I think you're all familiar with, 360 degrees in a circle. Each degree is broken into 60 arc minutes. Each minute is divided into 60 arc seconds. All right, so they did the same thing with the clock, and we'll talk about that in a moment. So that is, as I tell everybody, don't blame me, blame the Sumerians and the Babylonians. For some reason, they liked base 60, okay? And so that was their numbering system. And that may be because there are about 360 days in a year. 6 times 60 is 360. So there's lots of 6s in here. In fact, a number of calendars worked on a 360-day year. So you can imagine things got out of phase rather quickly. And so that's maybe why they just, decided to have 360 degrees in a circle. And breaking it into 6 parts comes out of the fact that you can take a radius, and I'm sure you've all done this, you draw a circle, and then you can take that radius and move it around 6 times. 1, 2, 3, 4, 5, 6. It fits perfectly. So that's where all this came from. We don't know for sure, but it certainly makes sense to us. So if you want to count in base 60, there it is. All right. What bothers me about this is 1 looks an awful lot like 60 as far as symbols are concerned. I guess it's context is what you've got to figure out there, okay? So if we compare the two, we work in both of them. We've got base 10, which is our basic numerical system, and we also work in base 60 when you're telling time or measuring angles, that sort of thing. So base 10, we've got 10 years in a decade, 100, 10 decades in a century, that sort of thing. And then money, of course, is broken down into tens. Base 60, we got time, 60 minutes in an hour, 60 seconds in a minute, that sort of thing. And then we did the same thing with angles. It's interesting that we kept the same designation, okay? Minutes and seconds. Okay, so a second is the fundamental unit of timekeeping. And this is where it gets interesting. Up until 1960, it was defined as 1/86,400th of a day. That's how many seconds there are in a day. Unfortunately, the rotation of the Earth isn't constant, and we'll talk about that in a minute. Between 1960 and 1967, I was alive when this all happened. I thought, this doesn't seem right. They did it as a period of a year, 1900. So how do you go back to 1900 to verify this? Okay, this didn't make sense to me at the time, so it only lasted for 7 years. Since 1967, this is when atomic clocks were invented, is defined at 9,192,631, maybe 192,631,777 periods of the hyperfine level transitions of the 133 cesium atom. Whoopee! It's the basis of the atomic clock. All right? And very, very stable. Stable for temperature, stable for everything. Okay? And so that's, how I won't go through how atomic clocks work. That's
Why cesium?
Because it was very predictable. I don't know exactly why they picked cesium, but maybe it's a little more stable temperature-wise. Could be. I'm just, I've asked that question but never found an answer for it. Okay? So this gave you an unvariable time base, which was nice. Trouble is, the Earth is slowing down its rotation, sort of. Recently has been speeding up. Don't quite understand why. It's not dark energy or anything like that, okay? But we'll eventually figure it out. But the big one is due to the tides. I think you all know that due to the tides, you get a bulge in the water. Because of the rotation of the Earth, it drags that around. And now that little bit of difference in gravity between the bulge and the moon is at a little bit of an angle. And that little bit of an angle is enough to slow the Earth down very by very little. And the conservation of energy means the moon has got to move further out in its orbit. So the moon is slowly spiraling away from us. So 350 million years ago, the day was 23 hours long. We lose a half a second a century in the rotation of the Earth. There's other things that kind of mess it up too, as you'll see some graphs that I'll show you. And the moon is moving away from us at 4 meters per century. So in a couple 100,000 years, we're not going to have any total eclipses. All right, the moon's going to be, way too far. Way too far away. So, because of this slight variation in the orbital motions, to try to coordinate things, we added leap seconds. Okay, we did that for a while. We're not doing that anymore. And I'll explain why. Okay, the last one was on December 31st, 2016. And so the clocks actually read 23 hours, 59 minutes, and 60 seconds. And then it clicked over to 0. So as I like to tell everybody, technically that was the longest day of your life, okay? I hope you use the extra time wisely.
Felt like it.
So, but we wanted to end the leap second thing, okay? So there was a general conference for weights and measures of all the various countries. It's an international body, and they decided that they were not going to do that anymore because it was messing up computer programs and all kinds of other things. All right? We'll talk about GPS time. GPS totally ignores the leap second thing. Okay? So they decided not to do anything with leap seconds for at least 100 years. And it's probably a good thing they did because the Earth appears to be speeding up a little bit, so maybe we're going to have to add some negative leap seconds if we were to do that. So it's like, don't mess with it till we figure out what all's going on here. So civil time and with the atomic clock and what have you is going to lose a little bit of synchronicity with the rotation of the Earth. It's not going to be exactly the same. So as I said, it caused serious malfunctions with computer systems, that sort of thing, when suddenly an extra second is introduced. Especially coordination with telecommunications and the grid system, because they got to make sure that everybody's working on the same sine wave, okay? And if you shift everything by a second, that kind of messes everything up. Yeah, it is. And as I said, Earth's rotation now seems to be speeding up over a short period of time. Here's what it looked like in 2020. This is the only one I could find the graph for. But you notice here it's a little slow. Here was the longest day. Here is the record for the shortest day. And then we beat the record again, and then beat that old record a third time. So the Earth is just varying in speed. In fact, when we have a major earthquake, NASA actually goes out and calculates, because the Earth shrank by maybe a meter or so, okay? Or part of the Earth shrank. And that, you've all seen, ice skaters, when they pull their arms in, everything spins faster. So if we have a major earthquake and it actually drops the radius of the Earth in one location by just maybe a meter or so, that's enough to affect the rotation of the Earth. Not much, but when we're measuring things to a billionth of a second, it's enough to affect that. So you've probably all seen this, okay? And if you look, they give you what's called the equation of time. That's this line here. Now, in this case, equation means reconciling things. It's not a formula like you see in your algebra class. And what it's telling you is whether the sun is ahead or behind. Right now it's behind. And then when it comes on this side, it's on the other side. And it actually looks like this, and it's the result of two overlapping issues that are going on with the Earth and the Earth's orbit. So they reflect two effects. And they're different and they're out of phase, and that's what messes it up. You have I think you all know that as the Earth's orbit is elliptical, so sometimes we're a little closer to the Earth and sometimes we're a little further. When we're closer to the sun, rather, the Earth is orbiting a little bit faster. And so that means that it takes a little longer for the sun to get on that meridian. And when we're further away, the Earth is moving a little bit slower, and so we actually get to the meridian a little earlier. And that's part of it that's reflected. And then, of course, the Earth's axis is tilted. And if you look at the sun along the equator, because this is going up like this, there's some changes in that time if you look at the geometry of it. Again, I won't go into the details there. So that gives you two things. This is the effect of the orbit's eccentricity, and this is due to the tilt of the orbit. And when you combine the two, you get this sort of thing. And that's what leads you to an analemma, which you've probably all seen images of. Okay, looks like that. If you go out at the same day, on the same time, maybe once a week or whatever, at the exact same time, and take an image of the sun, you get this figure 8 motion.
So what is that?
That's called an analemma, and it's due to the combination of these two motions. Okay, if you take this guy and this guy, you graph it like that, and then if you add, the same time of day all the time, you're going to get this sort of thing.
What was this other effect of?
So is that to where the Earth was round, or how?
What's that?
What does it represent how the Earth was round?
Yeah, this one here is due to the fact that when the Earth is closer to the sun, it's moving its orbit a little faster. And so if you can mentally picture this, here's the sun, this is noon, okay? And if I'm orbiting a little bit faster, I've got to rotate a little bit more to get the sun back in the center. So that means the sun is late. If I'm orbiting more slowly, I catch up to the sun a little bit earlier. And that's what this is. This one here has to do with the Earth's axis being tilted.
Right.
And that's the variance there.
This is what, there's a time in the winter here, I think where sunset stays almost the same for a long time, but sunrise changes a whole lot. That's been this phenomenon. Look, they don't change in tandem.
Right.
Sunrise and sunset.
I'd have to think about that one for a minute. Most likely it's hidden in here someplace, okay? But I couldn't be sure. Remember, in the wintertime, too, we're closer to the sun, or closer to the sun, so we're orbiting a little bit faster. So that's why you get this. That's where that comes from. Okay, so we get to the initial question. What time is it? Okay? And I don't know if you guys have ever heard the comment. You ask that guy what time it is and he tells you how to make a watch. I don't know if you ever heard that, but I'm that guy on steroids. Okay? Because now we have some questions. All right? There's local sundial time. That was the time humans used up to about 150 years ago. Okay? Then there's civil time. That's the time that you're used to. All right? It's now 26 minutes past 2 o'clock daylight savings time, Eastern Daylight Time. There's the initial International Atomic Clock Time, which runs just a little bit off of that. There is Universal Time, UT1. There's also a UT0 and a UT2. Okay, I'm not going to go into all of those. But that's the one that we use to compare these two together which leaves you coordinated universal time. If you ever listen to WWV, they come out and say, you know, tick, tick, tick at the tone, the time is going to be such and such, coordinated universal time. And that's an adjustment for the Earth's rotation and the atomic clocks. It's kind of an average between the two. And that's the, you know, the time we try to use all the time in astronomy. And then there's sidereal time. Yay. So, as I said, up until about 150 years ago, a little more than that, 175 years ago, everybody worked on sundial time. Even the town clock was set by a sundial. Okay? But when the railroads came in, and particularly the telegraph, how do you set a railroad schedule when every town is off just a little bit? And so that's why they set up time zones. That's where all that came from. And the other part of it was the telegraph. Now, you've all seen Westerns where the guy runs into the Western Union office and says, you know, send this off to Yuma right now, and this guy starts ticking things off. That didn't work, okay? It was a party line. Everybody was on it. So every station had their designated time to send messages. It's the way it worked. And so if everybody was on different times by a few minutes, can you imagine the mess? Okay, so that was the other reason. And we did it for the whole world. And so here's Greenwich, England. And so the time zone for Greenwich, England is Z. And so the military term for Z is Zulu. And if any of you have been in the military, know that the military works on Zulu time. If you're going to coordinate an attack on Baghdad or Tehran or wherever, okay, and you've got aircraft coming in from all over the world, how do you coordinate this? You got to be on one time frame. Also, most international corporations work on universal time. I don't know if any of you work for major international corporations, but how do you keep your orders straight? Okay, you're getting orders in Bangkok, you're getting orders in London, all this other stuff. And the only way you can do it is live on universal time. How do you coordinate that conference call between your New Delhi, London, and Tokyo offices? All right, if you try to figure out who's in what time zone and whether they're on daylight savings time or not, all right, you're better off just saying, you know, we're doing this at, 3 o'clock UT, all right? Which makes it about 11 o'clock at night here. So, astronomers, military, weather reports. I don't know if you've ever gone to Zippy, okay, or Skippy rather, that weather forecasting thing for astronomers. Their times are all in universal time. Clear Sky Chart actually calculates your local time. They don't do it in universal time. So government agencies, NASA, the International Space Station is all working on that sort of thing. All right. So I probably should have shown this slide a little bit earlier, but the difference between the sidereal time and the solar time, our 24-hour day, is because the Earth is orbiting the sun. So if this is the sun here, all right, that's noon. And as I'm going to try and do this without winding up, falling down, and being on YouTube. Okay, well, of course, he's recording it, so I will be on YouTube.
Yep, sorry.
Okay. So this is noon, and if I'm rotating and I'm also orbiting, now I've gone 360 degrees. Sun's not there. This is the true rotation, the sidereal time, the sidereal rate of the Earth. I've got to rotate just a little bit more to get that sun back in the center, and that's the difference is 4 minutes. And of course, as all you're aware, that works out to 2 hours a month. So, sidereal time is really local. All right, our sidereal clock at the Burrell Observatory is different than the one at Oberlin, is different from the one at Hiram rather. There are no time zones. Sidereal time and right ascension are related. I would hope that you all kind of know that the right ascension on the meridian is the local sidereal time. In fact, that's how you set up your setting circles. You put your telescope exactly on the meridian, making sure that declination axis is horizontal, and then you can set your right ascension circle to this local sidereal time. So a star with 2330 right ascension, if it's crossing the meridian, the local sidereal time is 2330. And there's no daylight savings time or anything like that. All right, so here's some of the other time bases that I referred to. All right, UT0, UT2, there's Greenwich Mean Sidereal Time, which I don't know who uses that. Greenwich Apparent Sidereal Time. There's Empress Time. If you look at some of the old Empresses, they don't use that one anymore, but they'll actually refer to Empress Time. That had to do with the orbit of the Earth rather than the rotation of the Earth. And then there's Terrestrial Time, Terrestrial Dynamic Time, terrestrial or barycentric dynamical time. That one takes into account relativity, okay, because the different planets and the different things are moving at different rates. And so that one takes in relativity. And then there's GPS time, which just clicks right along. It's basically atomic time. They don't worry about the leap seconds, so now it's 18 seconds ahead. But everything's adjusted for that, so that's why your stuff is still accurate. By the way, I should have probably put this up here, but I'm not talking about relativity. But if we didn't allow for relativity and the fact that the clocks are moving slower in space because of the lower gravity and are moving faster rather, and moving slower because of the motion, the GPS system would be pretty much useless after about a day. It'd be that far off if we didn't take into account general relativity.
Run that back again, please.
What's that?
Run that back what you just said. Here.
Oh, I said if on the GPS system, if we didn't take into account relativity, time dilation due to motion and gravity, the whole thing would be off enough that the thing would be useless after 24 hours.
Wow.
So we know Einstein was pretty much right. I always leave that little bit of doubt in. I always explain to my students, everybody thinks science is this surefire way to get an exact answer. And I tell them all the time, everything we know to a greater or lesser degree of certainty. One of these days I'm going to do a lecture on all the stuff we thought we knew at the beginning of the 20th century that we don't know now. Okay? I got an old book, an old physics book I bought in an antique store in London, and I bought it for two reasons. Number one, it had an entire chapter on caloric, which was that mysterious material that stuff that had temperature had, okay? Whereas temperature is a function of how fast everything's moving. It also had an entire chapter on the luminiferous ether, okay? Which was that, that stuff that permeated the universe that allowed light to go through, okay? That the Michelson-Morley experiment at Case Institute of Applied Science is what it was at the time, proved didn't exist.
What year was that book written?
1880 or something like that. Yeah, it was that was the only reason I bought it. All right, but a whole chapter, they expound on all this stuff they thought they knew. All right, so that brings up Siegel's law, and I kind of threw this in because this is really kind of cool. It's kind of a humorous, it addresses the pitfalls of having too much information. Okay, I've just given you a whole bunch of stuff. And basically what it says is a man with one watch knows what time it is. A man with two watches is never really sure. Okay, so let's talk about the days of the week and where those came from. Okay, Mesopotamians built these zigguats in 6000 BC. Okay, and they had 7 levels, each one for each of the moving objects in the sky. That's the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. And as you'll see, the names of the days of the week are named after them. We've kind of corrupted that in the English, but if you look at the Latin, it's really obvious. So that's where the 7 days of the week came from. So Sunday, we still hold that. It's Dies Solis in Latin, the day of the sun. Monday is the moon day, okay, dies lunae. Here's where it starts to get corrupted in the English language. Tuesday is actually, Tweesdag, which is the day of Tweeg, which is the god of single-handed combat. I don't know who created that god, but anyway, that's an old Norse, an old English god. Same with Wednesday. By the way, it was in Latin, it was Martes. Okay, if you've ever taken French or Spanish, these names still hold. So that was for Mars. Wednesday was for Mercury. Same, another proto-Germanic god. Same with Thursday. That was the god of thunder. All right, but it was for Jovis or Jupiter. That's where that one came from. And then Friday was for Venus. Again, an old English one. Again, the English we kind of corrupted all of that. And then we come back to Saturday, which was for Saturn. So that's where the 7 days of the week came from. I know some people might argue with me about, God's 7 days to make the earth and all that. I'm not going there. Not an argument I want to make. All right. All right. So what is a month? Linked to the phase of the moon. Sidereal month, remember, relative to the stars, 27.33 days. That's 2 consecutive crossings of the moon of a particular star. Synodic month means relative to the Earth is 29.5 days, and that's the time to any 2 phases. Any 2 of the same phases, full to full, crescent to crescent, new moon to new, whatever it might be. And of course, a calendar month is kind of close to that, because that's kind of how we decided that. So the reason for the differences is very similar to what I did with my little spinning around thing here, is let's start out here with a new moon, right in line with the sun, and as the moon is orbiting the Earth is moving in its orbit, and right here the moon has gone 360 degrees. It's gone a full revolution around the Earth. And so that's the 27.33 days. But we want to get back to the new moon, which means we've got to move this extra 27 degrees, or about 2 days. And so that's where the 29.5 comes in. That's the difference. You've all heard of a blue moon, okay? It has nothing to do with the beer or the song or anything else.
What did you just skip to a big paragraph?
What's that?
There's a big paragraph in the middle.
What are you talking about here? Yeah, I covered that. The additional 27.5 degrees takes about 2 days.
All right.
Okay? So, blue moon, all right? Synodic period is 29.5 days. If we have a full moon on the 1st of the month, and we're going to have the next one, it's going to be on the 30th or the 31st, depending on exactly what's going on. All right? So, the second full moon in a calendar month is called a blue moon. It has nothing to do with the color. I've actually had people come up to the observatory and say, I saw the blue moon the other day and it really was blue. No, it wasn't. Okay? It turns out that if you got a second full moon in the month before Lent, okay, it was considered a betrayer. And the Old English word for betrayer is Bellew. And so that was shortened to blue. So a second full moon in a month is a betrayer, or a Bellew month, or blue. All right? Happens on average once every 2.5 years, so once in a blue moon kind of works, Next one will be on May 31st, 2026. We had one a few years ago, which was really neat. It was on the 31st of December. Okay? End of the year. I really expected people predicting this is going to be the end of the world. But it didn't happen. They keep predicting it. One of these days they're going to be right. Okay? All right, the other thing that happens here with the moon is the orbit is tilted. It's also elliptical. Okay, so we have things that are varying all over the place. And it's tilted at about 5 degrees. And so the places where it crosses the Earth's orbit, those are called nodes. This is the ascending node because the moon is moving up. Here's the descending node because the moon is moving down. There won't be a quiz afterwards, so don't worry about it. Okay? And the moon's orbit is elliptical. So sometimes it's a little closer to us, sometimes it's a little further away. We got lucky on the last eclipse that it was pretty close to being, closest to us. The last one in 2017, it was actually very close to being further away from us. And so it was totality was under 2 minutes, I think, in most places. Okay, so there are other months. Okay, there's the tropical month, 27.3 whatever days. Okay, and that's the time between the same celestial longitude. That is a tropical month. An animalistic, and I keep calling it an animalistic, it's not the way, it's anomalistic, all right, month is 27.55 days on average, and that's the time the moon takes to go from perigee to perigee. Perigee is the closest position to the Earth. In an orbit around the Earth, apogee is the furthest, perigee is the closest, and because the moon's orbit precesses a little bit, that changes. And also this 5-degree tilt wobbles around, okay? Plus the Earth's axis is wobbling around. You add all this stuff up, you get all kinds of goofy stuff. So that's 27.55 days, and that's the time it takes to go from perigee to perigee. There's a draconic month or a nodal month, 27.21 days, and that's the time between going through the same node, the time it takes to go from the ascending node all the way around back to the next ascending node. All right, so that's a different month. So the next time you look at your calendar to figure out what month it is, good luck. All right, so what is a year? Okay, 365 days. Except when we have a leap year, it's 366, and that's every 4 years, except when the century changes and not divisible by 400. Okay? And I'll go through how that all happened in a minute. But there's the tropical year. All right, 365.242 days. That keeps us in synchronous with the seasons. Okay, if you go from equinox to equinox, that's the tropical year. That's 365.242 days. Then there's the sidereal year, the time between any two star alignments. And it's about 20 minutes longer than the tropical year. And that's due to the fact that the Earth's orbit, or the Earth's axis is precessing. It's wobbling around on its axis. So then there's the anomalistic year. That's to complete one revolution with respect to the perihelion or aphelion. Aphelion is the furthest part you are from the sun. Perihelion is the closest you are. And that's 365.259 days. And there's the draconic year. And that's an eclipse year or ecliptic year. And that's the time it takes the sun to go around to come up and line up with the same node. That's an eclipse year. And then there's a lunar year, which is 12 full cycles of the moon, which is really off, okay, by a lot, 354.36 days. Precession, I think you're familiar with, is the Earth's orbiting, the Earth wobbles around on its axis. It takes about 26,000 years for it to do it. Even with that, though, it causes us to update the grid system, right ascension declination every 50 years. But it's caused because the Earth is not a perfect sphere. It's got a bulge in the middle, okay? Like a lot of us. And because it's tilted, you got the moon pulling on it and the sun pulling on it, and that causes the whole thing to wobble around. So it's called precession of the equinoxes. And right now the pole is pointing at Polaris, but in 13,000 years, it's going to be pointing very, very close to Vega. So Vega will be the North Star. You can put that in your notebook so you don't miss it, okay? So here's what's going on. Back when the pyramids were built, Thurbin was the North Star. In fact, there's a couple of tunnels and stuff in a couple of the pyramids that line up with Thurbin. That's the way they were able to keep things in line. And so the grid system, right ascension declination, as you're aware, is the 0 point here is where the ecliptic crosses the equator. And because of this wobble, that shifts all the time. And again, this is why every 50 years, we've got to change the coordinate system. I've got a sure.
Planisphere.
No, not a planisphere, but a star atlas from 1950. Okay, and I've got one from 2000, and you can set them next to each other, and you can actually see how that pattern has moved. Okay, it's noticeable enough. If I make it another year, they'll come up with the 2050 ones. All right, they always do it on the halfway between, because you're never more than 25 years out on either side. And if I feel like it, I'll buy one just so I have all three. Okay. So again, it takes 26,000 years. That's why we have to update the atlases every 50 years. Okay. So now we got all kinds of different years. We got different days. We got different months. We got different seconds. Let's talk about where the calendar originated. Okay. Like so many things, it kind of inherited this from the Roman Empire, who kind of had inherited it from the Egyptians. Okay. Before 54 or 45 BC, all right, this is going to be a kind of surprise to you. The politicians manipulated the calendar for their political purposes. As things change, they all stay the same, okay? So they'd make the months longer so they didn't get kicked out early enough and all that other stuff, okay? So they changed the lengths of the months and what have you. The Roman calendar had 10 months in it, by the way. The Egyptian calendar had 12 months. And the Romans didn't use a calendar during the winter months. Don't know why, just that's the way it was. Okay? Julius Caesar's astronomers explained that they really need to move this to 12. Okay? We need to do the whole thing, okay? To keep in line with everything. And they needed to add a leap day every 4 days to keep things in sequence. Okay, that's where the leap year came from. And so they added the months of January and February because they didn't count the months during the winter time, so they had to add 2. So they added January and February. And the original 5th and 6th months were changed to July for Julius Caesar and August for Augustus Caesar. And because they wanted to make sure that these guys were properly noted, they made sure they had 31 days in each one of them. So they stole them from February. That's how February lost a couple of days. I mean, February was a new month. What the heck? He's the new kid on the block. We'll take a couple of days away from February. That was the plan. So here are the months as we know them. And again, we inherited the names from Rome. January is the Roman god of doors. I didn't know they had a god of doors, but they did. Okay, February 15th was celebrated the forgiveness of sins. Maybe that's why they wanted to make February a short month. They didn't want to mess with their sins too long, okay? They wanted to have more time to do them, I guess. March was for Mars, god of war, of course. April was Aprilis, and it was derived from, the opening of buds or whatever. Perhaps Aphrodite, the Greek name for Venus. May was the Roman god, mother of Mercury. June was the Roman goddess of love and marriage. Now you know why there's June brides, okay? That was the whole reason for that. July, I said, was named for Julius Caesar. Same with August, that was the 6th month. And this is where I don't know if any of you ever noticed this, but you'll notice it from now on. September, okay? Septa is the word for 7. September was the 7th month in the Roman calendar. It's actually the 9th month for us. That's because we added January and February. October was the 8th month, octo. Okay, that means 8. And it's, of course, the 10th month because we added January and February. November was the 9th month. That's where Nova came from. And December, that's 10. So I don't know if you ever noticed that, but the names don't agree with the number of the month. All right? Well, the Julian calendar was very similar to our own. You had 365 days. Every year that was divisible by 4, you added an extra day for a leap day. All right? That was assuming that there was 365.25 days in a year. Okay? The mean tropical year is a little less than that. So that meant too many leap days. All right? So the difference led to an extra day every 128 years. And that built up over time. And Pope Gregory in 1582 said, hey, we got to fix this. All right? And that gave rise to the Gregorian calendar. It was too many leap years. And so in 1582, Pope Gregory, with the help of his astronomers, introduced the Gregorian calendar as follows. This is the one that we're using today. First of all, 10 days were skipped in October. So October 3rd was followed by October 15th, okay, which made a lot of people really angry if you were paying by the month, okay? It was great if you were getting paid by the month, okay, but not so much the other way around, okay? An extra day was added for years divisible by 4, except years ending in 00, turns of the century. They had to be divisible by 400 for a leap year to show up. So that meant that 1900 was not a leap year, even though it's divisible by 4. The year 2000 was a leap year. It's divisible by 400. The year 2100 will not be a leap year. That made up for that little slight difference. And it's keeping pretty good track right now. We figure it's going to be off one day in 3,000 years. So 3,000 years from now, we'll kind of take a look at it and say, do we want to add another day or don't we? Okay? So, yeah, the year 4000 calendar will be about 0.8 to 1.1 days off, just depending on how much variance we have in the rotation of the Earth. As I said, a lot of people got angry when this whole thing happened. All right, well, the Roman Catholic nations of Europe adopted it immediately. Most of the other ones didn't. In fact, Greece was the last one in 1923. Finally adopted the Gregorian calendar. Okay? Orthodox churches still haven't adopted the Gregorian calendar. That's why Christmas in the Orthodox community is on January 7th and not December 25th. That's where that came from. Some religions are still using an old lunar or lunar solar calendar. And so Easter is determined as being from the old Hebrew calendar, is the first Sunday after the first moon, full moon, following the vernal equinox. So this year it was on March 31st. Passover begins, okay, on a very similar basis, the 15th day of the month of Nisan, which is essentially the full moon following the vernal equinox. So in many cases, Passover and Easter pretty much agree. This year they're off by a month, okay, actually 3 weeks because of that. Now you would have thought we would have, the Roman Catholic Church would have coordinated that because the whole thing of the crucifixion all happened during Passover, okay? So you would have thought that they would have coordinated that a little bit better, but they didn't. Okay, Rosh Hashanah is 163 days after the first day of Passover. The Islamic New Year, that shifts all the time. So this year it starts on July 7th. Ramadan, which is the whole month of fasting, that shifts again because they're working on a lunar calendar, which is 354 days. Okay, this year it started on March 10th and was done on April 10th. And the Chinese New Year is the second new moon after the winter solstice. So this year it was February 10th. And that's why that date moves. So, when the first calendars were published in 1640, everyone knew that their days were numbered. Okay, Julian days, let's touch on that. You're all familiar, I'm sure, with Julian days. It was a way it's another calendar to keep track of days so you don't have to remember that gee, was there a leap year between this and wasn't it, and all this other stuff. It's a count of days from January 1st, 4713 BC at 12 o'clock Universal Time. That was day 0, okay? That's where it all started. And it happens to be a connection between a 28-year lunar cycle, a 19-year cycle of golden numbers, whatever that was, I wasn't sure, and the 15-year Roman tax cycle. And when you kind of put all those together, they all converge on that date, so they decided that sounds like a good date to do it. So it's used primarily astronomers and software developers. Astronomers, because it's a lot easier just to subtract 2 numbers than to figure out how many days in this month and all this other stuff between events. And software developers that are looking for expiration dates and that sort of thing. So if you want to put an expiration date on something, it's a lot easier to just use Julian days to calculate it. So they were first introduced by Ludwig Idler. He was wrote a book in 1825 where he kind of suggested that, and it was really what John Herschel developed them for astronomical use in 1849 in his Outlines of Astronomy, and we've been kind of using them ever since. And so if you again look at the Stargazer's Almanac, they give you the Julian day here. And so there's a converter. Any of you variable star observers? Okay, the AAVSO wants your information on Julian days because that way they can keep the period of these stars, all right, without having to worry about, gee, did February have an extra day in it this year or whatever. Okay, they work on Julian days. So there's a calculator there, and you can put in the day and the time. So 2 p.m. when this lecture started, April 21st, 2024, was Julian day 2,460,422.04167. Okay, that was the Julian day. So, we're going to kind of end here the way we started. What's going to go through your mind the next time someone asks you, what time is it?
It depends.
It depends. You got that. Okay. So, I don't know if you guys have any questions. I'd be happy to try and answer them, or I'll guess.
I got a question.
Yeah.
Don't judge me, but I know the 10 digits gave you our
A base 10, yeah.
base 10. Now, what's base 12? Tell me that. What?
Okay, that's the number of joints in your hand, not counting your thumb.
Number of
1,
joints?
2, 3. Okay, you got bones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
For heaven's sakes.
That's where that came from.
There you go. Now I know.
Now we know.
Yeah. And base 60 came from 360 days in a year, and the fact that a radius fits around a circle 6 times.
There you go.
Is the Great Circle Mound in Newark has got some really interesting astronomical alignments.
Oh yeah?
Because the one opening, I think it's the furthest north that moonrise ever is.
Okay.
So it's whatever direction that is
Sure.
on the day that the moon rises.
Okay, now where's this mound?
That's the big Great Circle Mound in Newark.
Oh, okay. All right.
So that's pretty sophisticated bit of astronomy.
Yeah, well, what you wind up doing is just observing it all the time. They didn't have YouTube. They didn't have, any of this other stuff to distract them. So every time the moon rises, you put a stick in the ground.
Yeah, and the other mound, the octagon mound, I forget what it is, but it's got some real other different astronomical alignments.
Yeah, I think almost all of these monuments have got some sort of astronomical relationship with them because that's what people looked at. That's what it meant. Anything else?
They actually had a lot of stars to look at night, too.
Yeah, they had a lot more stars to look at night. Well, yeah, they could see more stars.
Right.
Okay? Yeah, unfortunately. It's the way it goes. Okay, guys, well, I thank you much. I hope you learned something. I hope I didn't confuse you totally.